For centuries, people have settled in large numbers where the land meets the sea, drawn by an abundance of resources and opportunities. Today, nearly 75% of the world's population lives within 50 kilometers of the ocean. Thus, coastal zones host critical ecosystems, infrastructure, and economic assets. So it's of growing concern that these narrow stretches of land are increasingly vulnerable to the dramatic effects of climate change, especially looking at the 2017 Atlantic hurricane season that was among the most intense ever recorded. Together, the six of us built a team to solve the challenge of the EY Open Science Data Challenge with the topic of 2024 being coastal resilience. We want to use AI for good, work with satellite data as part of a community solving societal and environmental problems through technology.
Moreover, in this case, we need to develop a machine learning and AI model using high resolution satellite imagery. Our goal to assess storm damage and support disaster response in typically data scarce coastal areas. When we talk about machine learning and AI, it's clear that the success of these technologies hinges on the quality of the training data, which makes image annotation indispensable. By labeling images with the precision, we equip AI to interpret these images correctly. During our annotation, we focus on four objects: damaged residential buildings, undamaged commercial buildings, and damaged commercial buildings. We took great care in aligning our criteria for using Label Me as a team, deciding on shapes, quantities, and the distinct features of commercial versus residential buildings. We are working to improve our AI model by adding external data that are clearly labeled, especially images of commercial buildings. This will help to model to recognize different kinds of buildings in much better way. We are also adjusting the training process of the model by changing the number of learning cycles and fine-tuning these settings. At the end, we want our model to be useful for helping places that get hit by natural disasters to get back on their feet faster and stronger.
Thank you, Fede, for explaining the challenge we faced throughout this project. Now, it's time to talk about how Team 6 approached the development of solutions for the project. Essentially, Team 6 followed two steps. First, we analyzed satellite images of San Juan, Puerto Rico, where the disaster occurred. Second, we ran a YOLO, you only look once model to obtain results. To analyze the data, we first set the geographical coordinates in San Juan. Then, considering the date when the hurricane occurred, we segmented our analysis into two parts, pre-event and post-event. From each part, we select three images. We visualize the red, green, and blue bands from the data, which help us to set how specific regions appear across different times and made it easier to analyze temporal challenges through the image. Then, we use a color code classification map. The main goal of this image was to identify portions of city vegetation and missing data. The last part of this process was to develop and normalize different vegetation index analysis to explore the health of the vegetation and to identify some of the anomalies. My peer Richa will give us detailed explanations of some of the visualizations mentioned. After all of this, we ran a YOLO model for object detection, and my peer Johan will tell us more about some of the results we have obtained. Over to you, Richa.
Next, we'll explore how enhanced satellite image analysis helps us monitor and understand changes in vegetation and other crucial environmental factors over time. Let's dive into our visual aids to better understand this process, starting with the image on the far left. First, we see an image utilizing the Centennial 2 SCL band classification. This color-coded method, shown here in vivid magenta and a spectrum of other colors, makes it easier to differentiate various land covers and conditions. For instance, vegetation appears in bright green, water bodies in blue, and bare ground in brown. These contrasting colors are not just visually striking, but they provide clear visual cues that help in quickly identifying areas of interest or concern, such as changes in vegetation density over time. Next, let's discuss the NDVI image. The NDVI, or Normalized Difference Vegetation Index, is a crucial tool in our analysis. It measures the density and health of vegetation by comparing the difference in near infrared, which vegetation strongly reflects, and red light, which vegetation absorbs. Here, areas of robust vegetation are displayed in rich greens, indicating healthy growth, while browner shades signify sparse or stressed vegetation. This allows for immediate assessment of vegetation health across large areas. Lastly, we look at the image to the right, the NDVI anomaly image. This powerful visual tool compares NDVI indices from two different periods, helping us spot changes and trends or anomalies over time. The color differences here highlight areas where vegetation health has improved or deteriorated, providing critical insights into the effects of environmental policies, climate change, or even natural events. These advanced imaging techniques enable not just the monitoring, but also the effective management of our planet's natural resources. Next, we'll dive into further analysis on our model and the data.
To build our object detection model for the identification of damaged and undamaged residential and commercial buildings, we used our own data and an external data set. That is because during this research, we only had 1 week to feed our model data, and annotating ourselves for 1 week is too short to build a precise model with a high MAP 50 score. So what we did is we annotated 130 pictures pre-event horizon and 25 pictures post-event horizon. We wanted to see our results, which are in here, the MAP 50 score, mean average precision 28, and see how we can improve this within our 1 week time frame. So we decided to move with the external data set, which the results are shown in this sheet, and scoring a great 0.76, yeah, 0.77 mean average precision, which is incredibly good. And that is because the external data were 5,000 pictures. We took a sample of 8,000 pictures, annotated concisely, consistently, and very accurate. Not that accurate, which causes overfitting, but in a more relaxed way, and this scored the 0.77 MAP 50 score, but we were unable to merge this data with our own data because of the YAML file, which was not directly linked. We couldn't adjust the YAML file in order to merge both data sets together. And this eventually, if we had more time, we could have increased our own score by annotating more consistently and more pictures in order to get a similar score like this. We move forward to the key insights and recommendations with Surima right now.
In these slides, I will talk about the key insights and recommendations. The results suggest that the model performs best with undamaged residential buildings potential due to a larger amount of training data in this category. However, it struggles most in recognized damaged commercial buildings. This suggests that the model is effective, but there is still a room for refinement. To enhance the performance of the model, several strategic actions can be considered. The actions addressed below aim to address specific shortcomings observed in model initial performance and further leverage advanced machine learning techniques and data management. The importance of dataset quality. A dataset has both of substantial quantity of instance across all categories, and precise labeling is crucial. The inclusion of diverse images, for example, different angles and accurate boundaries, enhances the model ability to formulate its understanding and detect objectives accuracy and the different conditionals. This emphasizes the need for careful data preparation and may involve using advanced tools for annotation to ensure high quality. In addition, the adjusting epochs and fine-tuning high parameters are very important. The third point is to ensure tourism remains profitable after hurricane disasters, given that one of the strongest sources of income in Puerto Rico is tourism, which accounts for 43% of the GDP and brings to the city more than 48 million annual. Team 6 will recommend that Puerto Rico will invest in a specific project to rebuild commercial buildings. This will ensure that the tourism continue visiting Puerto Rico and they could then enjoy local shops and restaurants in addition to still enjoy the incredible beach and landscapes that Puerto Rico offers. Thank you very much. That's the end of our presentation.